Okay, what I would like to talk today or to argue is of the need of lifelong learning when we talk about rapid and robust robotics, and especially when we talk about edge computing. So we had already introduction on swap computing, small of size, weight, and power. But what I would like to say is that it's not enough that we are robust there, we actually need to learn there. So let me walk you through that and my thought about it. So in general, people are telling us that AI has amazing capabilities, and we see how it's doing so well in identifying cats and playing games. At the same time, when we take the same type of AI to the outside world with Tesla and other cars, we see that it's not as robust as we wanted. And this is quite a large difference between, what we told and what we can do in a very structured environment and what happened when we take the AI outside in robotic and in autonomy. And I think that one of the reasons is that the paradigm that we have is that we have offline learning. So we kind of showing these examples, and then we see something else and we have to say how it's doing versus the thing that we trained off. And this is pretty much a paradigm. It works either in the first wave AI, in DARPA we call first wave AI, if something, then something, kind of like the 80s AI, or second wave AI, which is more like learning networks. But either way, we train the network before and then it's frozen and that's it. So the training is done in advance, or the learning is done, teaching done in advance. And when we see something else that is surprise, we usually wouldn't know what to do. Maybe it will be fatal, maybe it will not be fatal, but if we're unable to continue to learn on the go, we'll just do the same mistake over and over and over again, because we're now in the field and we're not open our ability to learn. So if there is some changes in the environment and we have to tune, we're unable to do it in classical AI. And this is a big problem when it's about robustness. In general, when we think about autonomy or robotics in the field, there is no way to prepare training set for all possible futures, and malfunctions will happen in uncertain circumstances. And that's why we see the classical thing that we improve with training, but then if we have a real change, we're unable to do that. We want to talk about this lifelong learning AI that has this capability to see that something is changing and we're not doing as well, and open up the training and the ability to online learn. So the question, how to do it smartly, and is it at all possible? So there are two reasons that we think it's possible. One, nature does it. Memory is doing reconsolidation, updating our memory. Bacteria is doing epigenetics. We have all these changes, and natural intelligence is really not about just doing robust thing that we learn, but about the ability to change program as we go. The other reason that we know that it's possible, we have a theory of computing that was suggested in the 90s. And the idea was that if we look at neural networks, at recurrent neural networks, and we look at the input that come in and output that goes out, and we ask, what does it compute? And the answer that I gave then was saying, well, if it's rational weights and they're not learning and not changing, then we have Turing machine. So if we have discrete computation, it's deterministic and it's pre-programmed, we have Turing machine. But it's enough to take one assumption off to already go to a whole another world. If we'll not talk about discrete, but something that is more continuum, if instead of deterministic, we'll have some smart type of nature, randomness or asynchronous. If instead of having everything pre-programmed, we'll allow the network to evolve or to lifelong learn, or perhaps we'll have like a series, kind of like saying, the brain at any point of time is like a Turing machine, it does a program. But when you meet me today and when you meet me after I saw the great talk of Michael Mangan, I'm already another person, I know something else, I don't have the same program, my program is a little bit better. So a series of Turing machine at every point of time, we use a Turing machine, but in between them, we update. All this give rise to super Turing computation, and supercomputation is really the foundation that there is something like lifelong learning. So with all that, I happened to be in DARPA in 2017 and offered this one of the largest efforts that was done. And the idea was that we'll have many groups together. And just to tell you, there are as many American as also non-American. We had people from Europe, from Middle East. We had very large groups, and we all tried together to think, should we look to neuroscience, to biology? What should we do to make this type of learning more possible? And we worked together as a very large group and came with a variety of solutions. I'll tell you very fast about two of them and continue with how we take it now into edge computing. So the idea of catastrophic forgetting is known, and since 2016 it was very well spoken, that if we learn one class, let's say to separate between 0 and 1, and then we learn another task, let's say to separate between 2 and 3, if we learn the first one, once we learn the second one, we'll become better in the second one and you'll forget the first one. And the reason is that if we train neural networks and we write on the same weights, it's clear that we learn the new one and forget the previous one. And this is really a big problem, because if we have large companies, you know, that have zillions of examples of writing, and then they made an accident and they want to teach about this accident, we don't want them to lose all the information that they had before, or to resort to what we used to do until a few years ago, to take the new information with the old information, to put it together and start learning from the beginning. It can take many months. So the idea was suggested by a bunch of companies and universities, and they say, you know, just use our method, which will be elastic weight consolidation, synaptic intelligence, or others. And if you use what we do, we'll be able to learn 0, 1, and then we'll be able to learn 2, 3, and we'll still remember as we go on more and more tasks, and we'll still be able to do them as good without forgetting them. So this sounds really good, but there was actually a problem. And the problem was that, because if you taught 0, 1, and then you taught 2, 3, and then you taught 4, 5, then the network could do very well each of them. But if you start learning that, and then we said, well, now I want to compare between 2 and 8, you know what happened? The network cannot do it because it's not a task. There was never a task that was learned like that. On the other hand, you'll agree with me that the network is really non-intelligent if it cannot take information from the different tasks that it puts and start putting them together. So we really want to have this lifelong learning that have the ability of streaming information, learn as we go, put together knowledge from different parts. If I learn something now, I want it to affect on things that I learned in the past, like if I learn to write, if I learned something, you know, about writing in a nice way, and I learned to write, you know, 30 years ago, so I want to put it together backward and forward, and I don't want to that somebody will tell me this is task 1, task 2. This is so unnatural. We don't have these things happen to us. So the idea that we suggested there is a kind of is a part of the group already in 2020. So this is like an old results that many steps continue after that. But the point was that the classical thing, we say we have a model, and if we want to have more things that we want to train on, we'll need to retrain it. But in reality, or in brain, we don't keep the previous information as is, you know, we don't have the same pictures that we saw. We already have some ideas in our brain, and now we have to learn something new. So it brings us to the notion of replay. You know, if we learn the first task, I learn how to recognize cats, and I have to ride bikes. So I can generate what I already know to do without all the details of how to do that. And this sounds really good, but you know, if you try generators, you know that they're really, really hard. Today with the when we go beyond GANs, it's a little bit better, but not yet. And the idea that we had, which is actually, I bring it because it has a point to the rest of the talk, is that instead of generating all the way to input, kind of like dreams, what we'll do, we'll generate just to high abstraction. And from there, we'll continue training with the new things. So whenever we want to remind ourselves things, we generate, but not all the way. And it's interesting because it really helps us to do better ability of putting things together and training. And the other idea that was seen in 2020 to be really useful was the notion of self-directed learning. So we have this picture, I can take a piece off and ask myself what should be here. And I know the answer because I have the picture somewhere. Well, I have exact colorization and I said, well, what should it be? And I know what it should be, and it's good. So we did a lot of that. And then Meta and some other companies started with the same ideas, that they wanted also to talk about self-supervision. But in general, the lifelong learning at that point is kind of like idea with many possible algorithms, but it gives us immersive applications, because now we can talk about mobile phone, about virtual augmented reality headset, and the ability that kind of we move our head on the go and we see that there is something here and something here and something here. And we don't have to learn a class by class. We learn as we go. And it really opened the world for also for local individualized machines that don't go to the cloud. So we can have privacy, which is something that we really like, but also something that is really surprising to us. We can actually start doing lifelong learning, which seems to be so hard because we think that learning is what takes so much energy, but there are ways to do that with actually low swap. So this is kind of something very interesting. We kind of ended, the program ended in 2022. I'm already back to academia a few years. And we started working in my lab of how to make this lifelong learning realistic, and especially realistic in changing environment. So the question is, can I take that into edge computing? Because if I had take it to edge computing, I have not only regular learning, I have better learning. And if I can, like what we saw with Michael is not special in the sense that, I mean, it's special and beautiful, but it's not special in the sense that almost everything that you see with low swap and is AI, it's actually trained before and was put on something that is very fast, like spiky neural network or something, and work outside. So what I would like to argue is that we need to have the learning on the go and that we can do that. So let me show you how we can do that. So just very lately, we introduced an algorithm, and this is an algorithm that is good for cheap hardware, edge computing, and for lifelong learning. We actually can add classes on the go and add things on the go. So what's the point? The point is this, and I want to put the names of Adam and Ed, which are working with me on that and developing, and we just kind of writing patents through the university about it. So we didn't want, but university wants some money. So the idea is this. If we think about backpropagation, the way that it works, we learn forward and then backward. So it means that when we put a pair or some group of pairs, we cannot just put in parallel a lot of inputs. It actually go one at a time, or group at a time, forward, backward. So it really freezes the machine. And this is very much unlike the brain to say, you know, I cannot work now. It's kind of unparalleled. It also requires expensive hardware because there is the weight symmetry going forward and going backward. Also, the neurons have to have local memories because they have to remember what was the output after we do all the way forward and all the way back. The error that comes back, we have to multiply it and compare it with our output. It's totally unsafe for online operation because the machine is frozen when it's training. So it's not really lifelong learning. And it stalls lifelong learning. We cannot consolidate new concept because we have to train in advance to all the possible classes. So we have this different algorithm. We call it signal propagation. And what we have is we have no separation between computing and inference. So we learn during the inference, more like the brain can work also on spiky networks, cheap hardware because no weight symmetry, no need to store neuronal output. It's safe for online operation because we never freeze it. We actually can do things in parallel, because as we start updating the first input output, or the first input in the environment, the next one is coming, the next one is coming. So as more and more input come, we kind of update and continue on the go. And it's appropriate for lifelong learning because we can consolidate new concepts without deciding only what will be the prior number of limits. So how does it work? It's actually, if you're thinking about it, it's not that complicated. So the idea is that in general, backprop, we have a neural network, and we have input comes from one side, and output, which is really kind of ridiculous type of output, it's more like labels, is on the other side. And the goal of learning the weights is the ability to take the input and to transform them through the network so it will fall on one of these funny labeled classes. Okay, so this is kind of as we talk about classification. So the idea that we have now, we don't want anymore to have input here and label output here. We want to have input and output both coming at the same side of the network. So both of them coming as input, and our job is to bring them together, just like we brought input to output together, but we can do it in a very nice way. So we put the input here, we put some transformation of the output here, and at every step we start bringing them together in a way that we compare what we have from the input, what we have is we transfer the output, what we need to change to the weights to bring them more together, and we go forward. So if we want to inference, we just go layer by layer. If as we go in the inference, we see that they seem to be very far, there seems to be something new, and they seem to be kind of so far from each other, then I'm update, but the update doesn't propagate back. I'm just update locally. So if it's some layer, I decide that I need to make some change, I make them locally and go forward. So that's the whole notion of signal propagation. And the idea is that instead of having classes as points in another label, we bring the classes labels to the same domain as the input, and it can be arbitrary points. As we go from step to step, we reach at the end that the inputs and the class label are similar and far from each other. And because of that, because it's all in this input domain, we didn't decide how many classes there be in advance. So if I start giving now, showing new pictures that don't fit here and don't fit here, I can just open a new one here, and zoom in and have better domain. So what we can add new classes, local update, no backprop path, perfect for on-device AI, and perfect for no memory chip. It's very interesting, I think, for hardware and biology, because what we show is that we can have global learning signals, kind of like targets or rewards. It can be, now we work in this summer, we work on this into reinforcement learning. So last year it was more for classes, and now we try to reinforcement learning. What we see is that we don't require backward edges, and we can have only local memory. So this is very interesting. I think both for hardware and for biology, it tells us that there are all kinds of capabilities that we can do with things that we thought that we needed, and we don't need them for that. So this is one point. We have this training algorithm that I would say, this really will allow us to do learning at the edge. So the second point that I want to suggest is what I would call better than reinforcement learning. And the idea that in reinforcement learning, you have an agent and it works in an environment. And usually we decide the time steps in a way that is kind of fit the environment. But, when we talk about people, sometimes we're in an environment and they will not fit, and we still usually manage to survive. So the question is, can we work in different time steps at the same time? And that's the idea, to have some kind of RL-like system that can work in different time steps, and we compare it, with regular RL and with temporal, as they called it, which is something that can learn with sequences. And we show that whichever way we take, if it's the time the jerk, which is very important on the number of decisions, we get something that is very good. I just show you one, but we have many examples. But the reason that I thought it's particularly interesting for this workshop, so I wanted to bring it, is if we have robotic movement, so you all know this walker, and this is kind of the best of RL. You see how funny it works. And if we have our walking, and it gives about the same return, but it comes with different trajectories and different walking. So you'll see it when it's not here, it's more clear to see that it uses more equally its capabilities. And the reason that it's done is in the algorithm, when we take this idea of multiple time steps, we actually take the jerk, not only of the simulator, but if it will be in real world, we'll take something about the jerk outside and minimize for that. So just minimizing for jerk, not by what we try, by what we get for the temporal features, it's something that is interesting. So I think I have 2 more minutes, and I want to ask Danish if I should stop here, or I should take the 2 minutes, or I should take questions here. What do you think is better?
I think 2 more minutes is okay for the audience as well. Yeah, 2 more minutes is fine.
Okay, great. So I just want to show you one more thing, is we have also another way of thinking about time, of what's happening around, in the sense of try to have temporal awareness. So in time series prediction, we have a lot of assumption that the input comes clearly and things like that. But we would like to have different class of neural networks that have temporal awareness and that can work with edge computing. And this is just a very simple example that if we have what we call dynamic weights and very cheap learning, it's a different learning than the one I showed you for here. We get ability to complete points and to have networks that are very small and train very fast and give good accuracy for prediction. And we try them for all kinds of things, for activity prediction and spatial temporal things. And it always will have improved training, better performance, smaller model. And I just want to finish the talk to suggest that perhaps in a few years, much of what we call AI won't be considered intelligent if we don't have really lifelong learning. And I want to say that it's also about going outside into the environment and being in robotics and in edge computing. So with that, I want to thank you very much. And thank you for inviting me for this very interesting workshop.